Our first afternoon speaker is Dr. Brian Anthony. He's Associate Director of MIT.nano. That's one of the largest lab or center in MIT. He's also the faculty leader of Industry Immersion program in mechanical engineering. His speech, he will basically share their latest research in machine learning and data science in process automation beyond robotics. Let's welcome Brian.
So normally, if I'm about to start a talk, I have to say good morning, good evening, good afternoon, depending on where you're joining us in the world. I guess we have some remote people. And if everybody can do this for a second, it'll seem like you're on Zoom, so I'll feel normal. Thank you for the invite, and thank you for your attendance today. Want to share a little bit about sort of the convergence of data science in manufacturing. I teach a couple different classes in manufacturing. And the way I demystify the opportunities for machine learning is that we've been doing machine learning, or things that are the predecessors for machine learning in manufacturing, for a long time. We've been doing real-time feedback control. We've been doing statistical process control. I want to take that up a little bit. So learned control. So what does that mean? In a manufacturing process, what are the inputs, what are the outputs? In is material and data. Out is modified material and more data. Control signals, set points, machines. The two that I'll highlight is a coffee roasting process and a fiber extrusion process. But the things that we'll talk about are very applicable to many processes. So control signals, machines, and products, and bringing together physical intuition and data intuition. So whether we're talking about coffee, when we're making coffee, we need to make dark roasts and light roasts. And historically, it can be challenging to have the appropriate controllers, the appropriate set points, the appropriate settings on your machine to go from a dark roast to a light roast very rapidly. So how do you make it faster and easier using the data that's collected during the normal manufacturing process to rapidly change your set point? Or if your material changes, can you, during the normal process of controls, acquire data that you can process at the edge so that you can learn something better about the process physics, about the machine, about the process? Fiber extruding. So again, same story. Set points of different materials, different properties, making it easier to control, to rapidly change the way dealing with material variation or machine variation or product spec variation. So just to frame coffee roasting, we're talking about big coffee roasters. Prior to COVID, I wanted to have a coffee roaster over in Building 35 on the corner of Vassar and Mass Ave. My coffee shop got thwarted with the pandemic. So when we talk about data, we're talking about something versus time. It could be pressure, gas flow, it could be forces and velocity. Data in, data out, material out. The canonical sort of problem when we think about feedback control, real-time process control, in the academic environment, often the canonical system that we go to when developing control systems or the things that our students like to do, we're going to think about robotic systems, which are important and powerful. But there are a whole slew of interesting processes that need to be controlled that aren't necessarily pick-and-place operations, but that are complex combinations of electromechanical actuators and material, where you have a set point, a thing that you're trying to control, whether that be a fixed parameter, like a diameter. I want to keep making a fiber of a fixed diameter. Or in the case of coffee roasting, when I'm roasting coffee, it's a recipe. I want to follow a temperature trajectory over time. And I want to do these things in a very repeatable, controlled way, in the way that I've designed these processes to operate. So we have a controller that's taking as input the error between what we want and what we get. That controller is then producing a signal that goes to our process, and it could be modulating a valve, making a drum go faster, actuating a robotic end effector. So the things we're trying to control as diverse as the types of products. So temperatures, speeds, diameters, dimensions. If you look at what is the entrenched standard, and rightfully so, of how real-time feedback control works, there's this thing called a PID controller. It's proportional integral derivative controller. If you don't know what that means, that's okay. But it's basically the idea that if I take an error, I have the thing that I want and the thing that I'm getting, I can choose how to exert control effort based on a signal that's proportional to my error, that's based on something that's proportional to the derivative of my error, or something that's also based on the integral of my error. Over 90%. Now that's sort of really very much the entrenched standard of how controls, real-time feedback controls are done and taught and used. And it's not going to go away, but we can probably do better. And there are places where it doesn't work very well. If we have processes that are particularly hard to model or hard to characterize, or that in the case of, for example, for a fiber, if you want to make a fiber that has a modulated diameter, and you would want to do that not for optical fiber communication, but you would want to do that in a scaled manufacturing process to integrate sensors, to make sensors that are integrated into a fiber. And whether you segment those fibers, those individual sensors, or use them as a long strand, there's some interesting reasons why you would want to, for example, modulate the diameter of a fiber. Now, modulating, or having multiple set points for a complex process like fiber draw, there's complex physics of mass transfer, of heat transfer. So the way that a PID controller works very well, the canonical, conventional way of controlling a robot or a fiber draw or coffee roasting, is to operate around a nominal set point, something that's linearized around a nominal set point. And it's hard, it takes time, a lot of labor, to then modify that set point to a new operating condition, whether that new operating condition is because of a new product spec or because the machine has changed in some way. So the question that we've asked is, how do we build on top of this entrenched architecture or sort of framework of real-time feedback control, and at the same time that we're controlling our process, how do we learn something about the process? How do we learn something about the physics, about the way this machine is working, or get a little bit more physical and data context for material variation, process variation? So we learn to control dynamic processes that are otherwise hard to model and do that in real time. And the difference is, you could do this now. You could have a controller controlling something, collecting data. You could store that data in a database, and then you could go and sit at your desk and collect the big data, because data can't be anything but big anymore, and process it and figure out what's the information that's embedded in there. Or we can bring some of the machine learning functionality, the deep learning functionality, to the edge, to where the controller is actually operating, and learn dynamically so that we can locally and rapidly improve our controller, but not have to have all that infrastructure that carts the data off someplace else. So the framework, we have time-varying control trajectories, temperatures, pressures, the signals that are the inputs to a machine. And that machine is making a product, coffee or fiber. We want to take that data and learn digital models of the machine, digital models of the physics, the digital twin. Right? A digital twin is nothing more than a model. Right? We've been using digital twins in engineering for a long time. To demystify it completely, I gave a whole talk last year, I think one of the first talks post-pandemic, or when the pandemic started, on what is a digital twin. Digital twin is just a model. Right? But how do we learn these models of physics, how to optimize, and how to make new variants when our machine changes? So if we take this flow that's on the screens behind me, and you just template match for a moment to the architecture, how we typically think about deep reinforcement learning. So reinforcement learning takes this idea of I'm trying to learn, I get a little piece of information, I do a little experiment, and I reinforce sort of my notion of what is working in the world based on sort of optimizing some parameter, sort of a performance metric. In the vernacular of deep reinforcement learning, you have some type of action operating on the world. The agent executes an action in the environment. The environment, in this case, being our manufacturing process. You get some reward, and that reward is, in our case, how well are we hitting the product spec? Are we maintaining the diameter that we want of the fiber, or the modulated diameter of the fiber? Or are we controlling the recipe, the heating up process of the coffee that's being roasted? Just to make it graphical. Right? So the agent is some controller, some algorithm, some computer system. Our environment is the manufacturing processes, and our reward is how well we're hitting the spec that we want. Now that's the simple diagram. The sort of the math-heavy diagram sort of maps to something like this. So don't spend too much time staring at the details. But if we look at this, this framework of we have an actor, we have a critic, we're learning at something. And if you take a control system lens to it, what you'll notice is that there's a piece here that is looking like a conventional controller. And then we've added a bunch of other stuff that's just locally logging and storing history and making modifications based on that history and doing something more than just making a real-time immediate decision. Right? But it's logging the data, but I don't want to just log the data and cart it out later. I want to log the data and make some decisions in real time. If we draw our control volume around that first piece, right, and then blow that up a little bit, this machine, this is a fiber draw or a schematic, a CAD drawing of a fiber draw process, taking some measurements of speeds and diameters and heat. And the actor is the control system. So this looks a lot like a conventional control system. We have some things that we're trying to control, the diameters, where we have some control effort from machines that are a motor rotating a spindle or pushing the core into the heater, or the drum that's spinning the coffee, providing both heat and mass, or heat and spinning the beans while they're roasting. And the plant is doing a thing. It's producing hopefully a diameter fiber of the thing we want, of the dimension that we want, measuring it and then feeding it back to the beginning. And that control system is trying to keep that set point at the place that we want. And then we have all the other pieces that are around there. We have sort of this history. This is a log. This is storing the data. We have some type of integrated into this. It's now sort of a reward function. So an integrated, the objective function of the thing that you want to optimize. Do you want to minimize your standard deviation, or do you want to minimize some balance of the variation at different frequency bands? But some notion of physically, what is the most important set of things to be optimizing? And then it's just taking that data now, and again, instead of carting it off later and doing your processing, digging a little bit more deeply, more richly into something beyond just modifying my control effort to achieve a set point, but let's take those data, what my set point is, the control efforts that I need to apply to get my machine to be in spec, to get the diameter that I want, to get the temperature that I want. And things are varying, and we're getting a controlled set point, but the way that we're getting a controlled thing is that there's a whole bunch of other stuff going on. There's variation in the current that's going to the motors, the voltages that are going to different heaters. So it really is, it's really the notion that we can bring to bear, bring to the front line, bring to the edge, the architecture of deep reinforcement learning, and sitting on top of and in real time with what we do for process control, feedback, real-time process control. Now the opportunities, the two big ones that we've deployed with some commercial partners already, is in this context of fiber draw. We're in the process of doing it with coffee. What this figure is trying to highlight that is, in practice, you already know approximately how the system operates if you have an existing as-built controller that's doing a fine job or a reasonable job in achieving the set point that you want. But with the architecture that we've developed, if you told the controller nothing, you say, well, let's just at least get fiber flowing if it's bad fiber. Let's get coffee roasting even if it tastes terrible, or the color is really bad. If we just turn the machine on, tell it the things that we want to do, over time, we've demonstrated that we can learn physical models of the system, and we can incorporate different levels of physics depending on how easily modelable the process is. But what this figure is highlighting that if over time, if we sort of turn the system on and it wasn't having any really intelligent control effort whatsoever, over time, depending on your learning rate and how much data is there, you could get to a point where your performance metric, the tolerance of the diameter that you're trying to get versus what you actually get, exceeds what you would get with a proportional integral derivative controller. Now in practice, you don't want to start from scratch, right? One of the big questions in deploying these things is, well, how many systems do we have that we can just start from scratch, that we're going to just turn it on and let magic happen? The reality is there are as-built systems that we need to integrate this into. So we'll talk about that in a moment. But this figure is for my students and myself, this is a very compelling and powerful figure. So let me explain why. If you think about fiber draw, I like fiber draw because it's both we were sponsored to look at it, but also it's a very rich pedagogical framework, and it's very simple conceptually. How do you achieve a fiber, the 125 micron fiber that is the backbone of optical communication? It's a mass flow problem. That's it. I have a big glass core that goes into the top of this fiber draw, and I have a tiny little fiber that comes out, and it's velocity and area in, velocity and area out. But it's complex in between. And so the dynamics, the fluid flow, the heat and mass transfer. And so what this is an example of, in this case where we're trying to modulate the diameter of a fiber, and for producing of integrated sensors inside of the fiber, our set point is not fixed. It's not just at 450 microns. That is a micron, right? Yeah, it's not just 450 microns. It's sort of 450, 500, 520, et cetera. And how can I, conceptually, how do I make a fiber thinner or fatter? Well, if all things be equal, if the input material is going at a fixed rate, I can pull it slower or faster. If I pull faster, it's going to get thinner. If I slow down, it's going to get thicker. Or I could push faster to make it thicker, or push the input material, the big glass ingot at the top, I could slow that down and get it thinner as well. So I can simultaneously push and pull on the two ends of this mass flow problem. And physically, so what is kind of cool, frankly, being a geeky engineer, is that what you're seeing here on the bottom is the learned. It learned this simple concept of mass flow, right? And it learned how to most optimally and rapidly, if I want to modulate my diameter that I'm getting, so I do this staircasing of diameter, I can simultaneously push and pull. And to write down from first principles and go through all that modeling that would actually sort of give you that optimal solution it's doable, but it's a PhD worth of work. As opposed to saying, hey, well, I can take the control signals that I actively use to keep a 500 micron fiber or 450 and learn from those little deviations. And those little deviations are enough information to make it so that I can learn how to do this very complex, simultaneous pushing and pulling to get this target thing that I want. And I think the next slide has the link or the reference to the paper, so you can hunt this down if you want to see more detail. And in it, we talk about we compare it to other control strategies, PI and QDMC as examples. So in this little nugget, and I have some additional things to share with you, it's a control strategy that doesn't require, it can benefit from, but doesn't require models to start, either analytical or numerical. It can benefit from it if you have it. Learns the physics, learns the principles of operation so that you can be faster at modifying your set point, or you can deal more rapidly with complex processes and changing your set points or recovering from breaks in that process. And this paper down there at the bottom, the dynamic control of a fiber manufacturing process, is the paper that came out earlier this year that has a lot of the detail here. But it's a very exciting area that would, if there are people in the audience that sort of have sort of problems in this interesting control space, would love to speak with you. But I'm pretty sure that one of the first questions would be, well, we have controllers from Siemens, from Rockwell, or things that we've done. How do we do this in top? Do we have to start from scratch? Do we just scrap everything, our current controllers, our present controllers, not current as in voltage and current, but so our present controllers. How do we do that? So the very practical thing is, okay, well, how do we deploy these things? We've developed this approach. We call it a connection point decomposition box model. But what that really means is, if we think about it in the context of fiber draw or coffee, we have a physical process, a physical mechanism, this black box. I purposely use black box as a black box modeling, but a black box that is something that's hard to model. This is, maybe it's a robot, maybe it's a fiber draw tower, maybe it's a coffee roaster. And that system currently, in your as-built framework, is being controlled with a series of controllers. And these could be PID controllers, PI, PD, QDMC, it could be, but they're controllers. The data we have, the only data we have, we can't take the system out of the control system and collect data. We're constrained. It's a real manufacturing process. We're not going to take it offline unless we have a pilot line to play with. Happy to take one of those. But we only can collect data at these points. After the controller has done its thing, we can imagine that we've isolated the system, get data at these points that are the inputs to the core of our process, and get measurements on the output. And we can also get measurements before and after the controller. One of the reasons this is really important is so as to not break your current process and to cautiously deploy these technologies into an existing line, we need to demonstrate to you that we're not going to break anything. Right? So let's first model the as-built system, demonstrate that in silicon on the computer, we can simulate that closed-loop system. And then once we have that working, then we can sort of say, okay, well, we trust with our closed-loop simulation working, with the models that we've developed for both the process and the controllers, we can then start to play around with the controllers, predict what the controller performance improvements would be, and then cautiously deploy those. So in the interest of time, I'll sort of skip through that for a second. But so we have a process that works very well in the 3 cases that we've worked well with it, to decompose something that's already deployed. And we've done this on fiber and on coffee, and more recently on a packaging process. So again, integrating deep reinforcement learning at the edge, and have a strategy by which we can, recognizing the constraints of the manufacturing environment, not have to start from scratch and do this in a cautious way. So the other little nugget, 2 other nuggets I want to share. One on data and privacy, and another bit, as time allows, and we'll have the panel as well, on education and workforce development and training. The context, you probably can't have not heard about either digital manufacturing or smart manufacturing, Industry 4.0. It's in the press all the time. It's manufacturing, but with a lot more data, a lot more sensors. So we're exploring, under the recognition that not every manufacturing enterprise they have manufacturing engineers, they have the people that know the physical process. You're probably missing the people that are the data scientists, because the world is recruiting them. So how do we make it, what are the opportunities for technology to make it easier for manufacturers, or anybody for that matter, to share their data or aggregate their data? So what are we doing? So let me explain first. So homomorphic encryption is an encryption technology that allows us to do math in an end-to-end encrypted way. So that means I could take the number 2 and I could take the number 3. I could encrypt them. I could give them to you. And you could do math. You could add those 2 encrypted numbers together. I think I gave you 2 and 3. So you'd get an encrypted 5. But you wouldn't know that it was a 5. You would have some encrypted garbly thing. And if you gave that back to me, I have the key. I can unlock it and know that it's a 5. Now, the ability to do that is constrained by how many mathematical operations you need to do to add. Maybe you need to add 2 and 3, and then you're going to multiply it or square it, and you're going to do a series of operations of the sort that you would need to do in a machine learning algorithm. You accumulate noise as you're doing this. So there's a limit with how many mathematical operations you can do. But so this thing called homomorphic encryption is this nice way to give this end-to-end sort of encryption. And how we're using this in the manufacturing enterprise is, well, the premise is that maybe you don't have the internal resources to do the data science, and maybe you're uncomfortable sharing your completely secret sauce, even if you have contractual protections in place. So let's give you the extra confidence that you can share your data, have somebody else do the data science without actually ever really seeing the real numbers, either the input or the output, and I can get those real numbers. The other context, the other opportunity is, well, are there situations where there's a benefit in different industries, or with we'll pick on robots for a moment, where I actually would benefit from aggregating my data with your data, with my colleagues' data, and I want to only share aspects about the machine and not the recipe, or not how I'm using the machine. So there's some benefit from uniformly encrypting and then aggregating the data. I'll skip that slide. I have clouds to demonstrate, or to denote that to pay attention to the details, not at all. You can see the slides later. So this locked learning, so we call this thing locked learning, and really what it is this idea, again, of I take numbers, I put them into a higher dimensional space, I turn them into a polynomial. The punchline, though, is really I use this example of 2 and 3. It's, again, you don't need to go into the details of the math, but it's this idea that I can encrypt, do math on the encrypted things, get an encrypted answer, and only when I give it back to the person who really owns the answer could they decrypt that and get the 5 in this case. Okay, so there's a nice paper out, and just because we have the data and it's a convenient demonstrable process, the paper that we put out that sort of highlights the opportunity for this in the context in particular of small and medium enterprises that may have interest in outsourcing their condition monitoring or the metrics that need to be determined to do predictive maintenance. This paper, Homomorphic Encryption in a Secure Preventative Health Maintenance Outsourcing Solution, talks a lot more about the details of this. So I have 4 minutes left, which should be good. The last little vignette that I want to share with you is I happen to benefit from the spoils of MIT in that we don't have to recruit the best I don't have to recruit the best and the brightest. MIT does that for me, and I get to collaborate with them to my advantage. So education and training, it's easy for us to do it here, but we also need to sort of educate the world. So it is our mandate. But more broadly, in the context of manufacturing, it's very helpful to be in a factory. Before I came back to MIT, I crawled around for a decade installing high-speed video systems for process control. But it's helpful to be in the factory. So we have this degree program called the M-Engine Manufacturing, which is a 1-year degree program that historically has taught students sort of these 4 pillars of manufacturing design, manufacturing systems, so what happens inside the 4 walls of the factory, and manufacturing operations and outside the supply chain, and then design and a little bit of business. Now, within my home department is mechanical engineering, but I'm a mechanical engineer, computer scientist, and we see there's a lot of demand, a lot of interest across all of our students. The reason that MIT created the new college for computing is because of the massive demand in computing that ends up in all domains. So what does computing mean to a mechanical engineer, to a manufacturing engineer? So I'm interested certainly in the manufacturing side, and then more broadly in mechanical engineering. One of the exciting things that we're doing, in the context of this degree program, this 1-year program that the students do an applied group project for their thesis. It's a little bit different than the sort of a research project on campus. We place groups of 3 students into companies solving a sort of in the line of fire design manufacturing problem. This year and next, to inform the department, is there a need, there's a need, I think, my bias, and there's an opportunity to add I'll call it a 5th year, but sort of another layer opportunity of adding data science in appropriate ways to the curriculum, an undergraduate curriculum of mechanical engineering. But we're able to pilot this right now, and having the projects that we do, the projects that we're recruiting for this 1-year degree program, be at least part of them, so we're looking for about 10 projects this year, having them be very data science, machine learning centric, right, to sort of get some additional experience as a department. We know this is the right thing to do for this degree program, but to inform whether or not we should be doing something like this for the entire department. So I guess it's just very interested in collaborating and very interested in working with you both from a research side, but if you have these sort of in the line of fire projects that would benefit from a talented group of 3 students that have both a mechanical engineering and manufacturing bearing and an appreciation and a lot of usage experience, with data science, machine learning, we're looking to define those projects with you. I guess the last thing, and I think you heard from professional education earlier today, so that's something we do on campus. Going back a long time, now 5 or 6 years ago, we had a very interesting long collaboration with Arconic, formerly known as Alcoa, where during a summer program, we brought 40 of their plant managers to campus, and they came from engineering backgrounds, finance backgrounds, and really level set them in sort of the fundamental underpinnings of what it means, what is smart manufacturing or digital or IoT. That has led to then sort of a really interesting proliferation of some of the online classes that MIT offers. In particular, I teach one in smart manufacturing and one in industrial Internet of Things. I'm not doing this for shameless promotion, although I guess I really am doing shameless promotion, but it's more sort of the context of, well, how do we actually make sure that the things that we're developing, the pathway to get these things out is through our students, but also working with you in strategic ways, both sort of in the can material, but working closely for custom programs that are custom designed for the workforce and the people that you have in your enterprises. And with that, I'll skip through those last 2 slides. I've got the 0, mark. Thank you for your time. Just wanted to share a little bit about sort of how we're applying deep reinforcement learning at the edge, some of the unique opportunities when you start to fuse machine learning and encryption, and none of this is possible without the students and without you. So thank you, and happy to take some questions. Oh, there's questions there. Got it. Okay, what would you say that are the downside of this method? Why are over 90% of the industry still using PI? So PIDs, so the question is, people are seeing it. Why? It works very well. I'm not trying to say that our techniques are going to get rid of a conventional controller, but there are places where it doesn't work well. If you have these dynamic set points, or it takes a lot of time, even with a PID controller, if to sort of retune. If something's working well, how do you, and the material changes or your design specs change, it takes a lot of time and effort to sort of retune and re-optimize your PID controller. There are strategies for that. We're trying to accelerate that, make it easier. So maybe the thing we do is just to actually make a faster way to automatically retune the PID controller. And the other downside is, it is certainly more complex computationally, mathematically. Level of sophistication at the edge control be needed to implement such machine learning versus the extremely cheap PID controllers that exist today. Yeah, so if I understand the level of sophistication, so maybe the question is related to the compute power. The compute power is not, it's certainly a little more than what you would get in your conventional PLC, your conventional programmable logic controller. But it's not a lot more complex than what you would get in sort of what you would need and come out of an Android or pick your small little compute platform of choice. The thing we're leveraging, why am I having this conversation with company after company after company? Why smart, why digital, why IoT now? We've been doing these things. Process control, whether it be feedback or real time, is machine learning. It's an aspect, it fits within the framework. But we have cheaper processors, we have more data, better sensors, right? And better communication to get the data from point A to point B. So it's really amplifying what we've been doing in a more cost-effective way. So yes, it's a little bit more sophisticated, but it's not, and certainly the workforce, and those are pieces of the ecosystem that need to be addressed. But it's not outlandish at all in terms of the compute power or the effort, the intellectual effort that goes into deploying a controller such as this. Okay. How do we know if we are accurately representing our specification of our physical world and creating a full representation of all the important qualities of the material product? Yeah. Well, the flippant answer is we're never really going to know. So the more rigorous answer is, certainly in the context of things that we do in the lab, we can do the controlled experiments to verify that the approach is working. But I guess maybe the other way to look at this, often, how do you tackle a smart manufacturing or digital or an IoT manufacturing problem? You need to take this parallel approach. What's the physical context? you have intuition. You have intuition for fiber draw. It's just mass flow. It's a simple intuition. The devil's in the details. Right? So often there's going to be at least physical intuition that says, hey, well, the model is predicting, the thing we've learned predicts this. As long as that jives with your intuition, hopefully you have some intuition. You should be having intuition if you're using that process. So I think that's probably the more, not quite rigorous, but sort of more sort of realistic answer is if the models you're learning and the process the intuition that the model is telling you, if that agrees, at least in some way, with what your physical intuition is telling you, then you have some confidence. But then you should do experiments, and you should proceed cautiously as well. How could dynamic control work within a good manufacturing process environment? How could batch records be generated? Let's see. So let's see, batch records. Don't have a really good answer off the top of my head. But so dynamic control, so I mean, any place where certainly there's a lot of the models are not hiding things. They are sort of documentable and capturable. You can sort of capture and explain what they're doing. So you have that record and archive of what they're doing. And there are different types of processes, whether we're talking something that's continuous time or batch or someplace in between. So it kind of depends on the particular process that you're talking about. So happy to follow up with whoever asked that question afterwards. Can you apply this process for retrofits by using the deep reinforcement learning model to dynamically model the set points of the existing control systems? Yes. Yeah, sort of the slides that I skimmed through, this idea of retrofitting where we can, the mechanism that we've deployed is, so there's the existing as-built system with the PLCs, the programmable logic controllers, doing the control thing that they do, using PID. And then we have another computer system that sits back behind it that's basically injecting into it dynamically, at whatever rate is allowable by that particular controller, modifications to the gain settings and how that controller operates. So that's one of the easy mechanisms by which we've just add a little additional intelligence onto that existing control structure to implement and practice these things that we're developing. Okay. Okay, thank you.